Okay, hi everyone. Today, our last lecture, I'm planning to just summarize and go over kind of everything that was in the course. I thought it would be nice to give an overview rather than going into some new topic. So this is what we will do. So we started by talking about a graph expansion. This was like the starting point for high-dimensional expanders. And in graphs, an expander graph is a graph that is both sparse and very well connected, and we defined the Chigger constant, or the edge expansion, which was the minimum over all sets of vertices that are not empty and that are less than half, say, of the vertex set. The minimum of the number of edges between S and S complement divided by the size of S. And the set that minimizes this quantity is a bottleneck. It's a set that doesn't have many edges going out compared to its size. And a graph is a very good expander when this number is actually close to 1. I guess I should think of a d-regular graph and normalize by d. So this was the one kind of natural way to think about graph expansion. And then we said that it generalizes to, that there are many ways to understand graph expansion, and each of them generalizes to a different notion. So the three ways was, one was spectral. There are many more than just three, but these are the ones that we focused on. The other one was random walk, talking about how walking on the graph, how fast it takes you to reach a uniform distribution, or near uniform. And the third one, which was really kind of more separate than the other two, let me call it cohomological. And it had to do with more like linear algebra over a finite field over F2, and you could think of it as topological. And these two are more together. So the spectral definition pretty much talks about the adjacency matrix of the graph, let me call it M, as being approximately equal to the all ones matrix, which is, you can think of it as the adjacency matrix of the clique graph, the dense complete graph. And when I say this approximate, we said that the norm of this operator is at most some small lambda. And this is one way to say that M is an expander. It's equivalent to saying that the second largest eigenvalue of this guy is at most lambda. So this is a, let's think of it as a spectral way of saying that our graph is a pseudo, this graph, which I call pseudo-dense. People usually say that it's pseudo-random. I guess not so many markers. But thinking forward to the high-dimensional case, it's not going to remain pseudo-random. It's going to become pseudo, like close to something, and that something is like the complete graph. So this is the complete graph, and this is our sparse approximation, which is the expander. Okay, and so one way to understand this definition is to say that an expander is sparse, but it behaves as if it were dense. Its connectivity is as if it's dense. Then we also talked about random walks, and we said that fast mixing, a random walk on such a graph is fast mixing. And then we talked about this more cohomological definition, and in this definition we were looking at the graph, the geometric object, and interpreting it as if it's like a set of linear equations. So we are thinking of assigning values to, say, the vertices, and having the edges say that, the XOR of these two values needs to be 0. So then if you think about it that way, you define the coboundary expansion of a graph to be the minimum over all functions from the vertices to Z2. So this is just like looking at subsets of the vertices, so it's the same. And then in the numerator, you measure how many edges XOR to non-zero. So delta F on an edge just XORs the values on the two endpoints. And we measured this, and in the denominator we said we divide by the distance of F to, in this case it was either the constant 0 function or the constant 1 function. So I'll remind it a bit more later, but we had this kind of expression that is exactly identical to this expression. Okay, modulo, you can make it really identical, and but writing it in this bizarre way, it puts it in a cohomological framework, and then we said we can generalize it to higher dimensions. So these were kind of the three kinds of expansions, and as I said, really these two kind of are the same sort, and this turns out to be of a different sort, I think. Yeah. Okay, so then we move to talk about high-dimensional expanders. So the first thing we talked about was the concept of a link. Okay, so we have in mind a complex X, which has vertices x0, edges x1, triangles maybe x2, and so on. And then we said that the link is a part of this complex. So we have some picture in mind. Say I can draw some complex like this, and then the link of a vertex, you look just at the parts which are either edges or triangles that contain this vertex. So here I'm thinking of also having this triangle. So for example, the link of this vertex was all the triangles that contain this vertex, you take their edges, and all the edges that contains this vertex, you take the vertex. So I only have here blue, blue, and blue. Okay, here's also red. So we had this vertex V, and then we took these guys are going to be the vertices in the link of V, and these guys are going to be the edges in the link of V. So in this picture, the link of V turned out to be a disconnected graph. So the link of V is just this graph. And this concept was interesting. It's something that became very central in this course, and it really allows you to talk about important and interesting subparts of this object, and also it allows you to condition. It's like you say, oh, the complex conditioned on containing V. And then for simplicity, you removed V from the object, and you're left with what's interesting now. So this is the link of V. And our first definition of expansion, so here is a black one. So our first definition of expansion was the definition of link expansion. X is a gamma HDX. In the link expansion definition, if it is a, well, let me just say, well, it is connected. Maybe I don't need it, and B, links of all S in xi for I less than the dimension of x minus 1. So, for example, if x is two-dimensional, then 2 minus 1 is 1, I less than 1, so all I is 0. So this is for all the vertices, the links of all the faces in the 2 dimensions below the top dimension are have a gamma expanding 1 skeletons. So the 1 skeleton is just, you look at the link. The link doesn't have to be just a graph like it is here. It can be higher dimensional. You only look at the vertices and the edges. That's your 1 skeleton, and you want this thing to be a gamma expander, right? So in my picture, the link of V is not a gamma expander. It's not even connected. But if all the links were connected, then this thing would be an HDX. And really, if you allow I to be even minus 1, so even the link of the empty set, then the underlying graph should be an expander. But if not, then you need these two things. So that was our definition. And we saw that if you play around with it and you try to draw for yourself a complex like I just did on the board, and you hope to make it an HDX, then you will soon make it very dense. So if I try to make the link of V an HDX, I would need to add a triangle either connecting, for example, these two vertices, or maybe connecting these two vertices. So I can add that triangle, but then the link of this vertex, for example, grows because I added one more neighbor. And if I keep doing it, somehow I don't know how to do it greedily in a way that makes the links expand and at the same time makes the degree of each vertex and edge constant. So I don't know of such a construction. This would be fantastic if someone can come up with a construction based on elementary operations. We have several constructions that we've seen, and I'll remind us some of them soon. But I wanted to say something, now I lost my train of thought. Okay. So we saw that constructing sparse HDX is non-trivial. We also saw that the random doesn't work. There's no way we know how to set like an Erdős-Renyi model to keep it sparse. If it's dense, then it's okay. You can do it, but you cannot do it sparsely. And then we saw this really nice trickle-down theorem. Remember this theorem? It was about connecting local to global expansion. So it says local expansion implies global expansion. Namely, for example, even in this definition, if you have a complex, for example, a two-dimensional complex, and it's connected, and you know that all the links are expanding of the vertices, then you can deduce that the entire graph is an expander. And this was not a hard proof, but very unusual and very kind of surprising, I think. You're given a lot of information about local pieces, and you deduce a global expansion. So that's really nice. Okay, so this theorem, we saw it. It's due to Oppenheim, and we also mentioned that it relates to much earlier works of Garland. And the way we proved it is by analyzing, you want to analyze the spectral expansion of the entire graph, and you write it as like a sum, and you break it down into pieces depending on the links. And from the expansion in the links, you can recover the expansion, the global expansion. So that was link expansion. Then we moved to talk about up and down operators. Right, so we had this, so the first notion that was kind of very important is this notion of the link, and the second notion that was very important is the up and down operators. Right, and these operators, you take a function on the I faces, and the up operator moves it to a function on the I plus 1 faces. So let me say that the up takes me from Ci of x to Ci plus 1 of x. So this is just a notation for functions on the I-dimensional faces of x. And the down operator is the opposite. It takes me from Ci plus 1 of x to, well, let me call it Ci, to Ci minus 1 of x. And the way they were defined is that up on f at a certain point s, now s is in I plus 1 face, because the up of f is an element in Ci plus 1, and it's just taking the expectation over all the faces just one below s and taking f of t. And similarly, d of f was we saw that it's the adjoint operator, so let me call this guy t actually. So now if I have a function g on the I, actually let me add a plus 1 here so I'm on the same spaces. So now g is on the I plus 1, and I take down, so dg is an element on the I faces, and dg at the point t is just the expectation over all s bigger than t just by 1 of g of s. Is this correct? Wait, let me see. Yes. Okay. And we also saw that really there's a way to think of this as a bipartite graph. Here you have xi plus 1. Here you have xi. And you just put a vertex here for every I plus 1 face, and a vertex here for every I face. And you connect these by an edge if this I face is contained in this I plus 1 face. So you get a bipartite adjacency graph, and then this operator is really just the adjacency operator of this matrix. You take a function on this side, and the up operator gives you a function on that side. And conversely, if you start from a function on this side, the down operator gives you a function on this side, just by averaging. Okay, so this is like a geometric picture of the up and down, and this also shows how they are jointed to one another. If you look at the inner product, you can write that the expectation of UF comma G is equal to F dg, and in the middle you get the expectation over all S bigger than T, over all pairs S and T. So it's basically over all edges here of F of T, G of S, I guess. So this shows you how D and F are kind of adjoint to one another. Okay, I mean, we tried to, we kind of started playing with these operators and understanding how they correspond to random walks, for example, moving from vertex to vertex, or edge to triangle to edge, all kinds of random walks. And we started understanding what the spectral behavior of these operators is. We came up with this definition, let's call it random walk. Random walk expansion, which is supposed to be, I guess, analogous or compared to the definition of link expansion. And here you want to say that a complex X is I don't know, beta HDX if, and now we said something like, if I walk from an edge to a triangle to another edge, it should be similar to walking from an edge to a vertex to another edge. Basically, we were comparing the walk of going up and then down compared to the walk of going down and then up. Okay, so let's think about it on edges. From an edge, you can either go to a triangle and back to an edge, or you can go to a vertex and back to an edge. So I'm going to write the definition soon. Let me actually leave space here. But the definition is going to say, okay, let me write it. If UD minus DU minus, there's going to be some, not beta, some number, I don't know, R times the identity, for some R, for some Ri. So now here I need to say, I want this definition to hold for all levels. So if I'm going up from I, then I'm going to go back down from I plus 1, or if I can go down from I and back up from I minus 1. For some numbers Ri, and for all I less than the dimension of the complex. So if I'm a two-dimensional complex and I have triangles, then I can only go up from edges. I cannot, if I was the top dimension, there's no place for me to go up. Okay, so as long as I have room to go up, I want that the up-down operator is the same as the down-up operator. Now, for some reason, we had to add this part. Do you remember why? Thank you. Yeah, so there was this issue of laziness. So Ri accounts for laziness. Because, for example, if you go up from a vertex to an edge, and now you go back down, you have probability 1/2 of returning to where you started. So really the up-down walk in a graph corresponds to probability 1/2 staying in place and probability 1/2 going to the neighbor. If you think of M as the adjacency matrix, then the up-down walk is this in a graph. Let me call it up from 0 to 1 and then down from 1 to 0. So when we say that an expander graph is a good spectral expander, we interpret it to say that this part, not both together, just this part, is very close spectrally to the complete complex. Right? This was my definition all the way up there. We said that M is almost like J, up to some lambda. So also here, I want to say that M is also like J. So instead of the up-down, I'm going to write up-down minus this part. Just move half identity to this side. Basically, I can rewrite this as saying 2 times du equal minus the identity equals M. I just rearranged. Okay. So up to multiplying by some scalar, I get this to be, this is like half M. And this, what is the down-up operator on a graph? You go from a vertex down, you basically reach the empty set, and you go back up, you reach another vertex. So the adjacency matrix of the down-up walk in a graph is just J, right? So up to this normalization, for a regular classical graph, you get here just the j minus m is very small, and for high-dimensional expanders, we just increase the dimensions. Okay, here is it.
There should be some normalization factor on du also, is that right?
Maybe I need some number here, you mean?
Yeah.
Okay, thanks, sure. For some r.
It's not a global scaling.
Yeah, you're right. Okay.
It should be like 1 minus ri, right?
In this case, but I think it doesn't matter because you can always divide by alpha plus r everything. So, not sure, but let's not worry about it. So that's the definition of random walk expansion. And we also saw, that two things. First of all, that I didn't, in this summary, I didn't kind of go into the subtlety of two-sided expansion versus one-sided. This is all two-sided. So in this case, a random walk expansion is qualitatively equivalent to link expansion. Of course, in one direction you lose something in the constant. So sometimes this is important. Other times it's less important. And we saw this nice, beautiful application to mixing of random walks on matroids, on matroid bases. I don't know if you remember this, but we gave some examples where you want to prove fast mixing because you have some exponentially huge graph, and you want to understand, you want to sample some random element, for example, shuffle a deck of cards, and then you want to reach some random location in the graph. You want to know if your random walk is mixing. So one example is if you're given a matroid, you want to sample a random basis. And an example for that was look at all the spanning trees in a given graph and give me a random spanning tree. And the idea was start with an arbitrary spanning tree and then randomly erase an edge and randomly add an edge and keep going. And we wanted to understand how fast this is mixing, and we saw that, people didn't know how to solve it until they realized through this direction that this complicated graph is much easier to understand if you realize that it's not just a graph. It's not a graph whose vertices are trees. Rather, you should think of the appropriate HDX where the ground set is the edges of the graph. So you want to sample, spanning trees in some graph. You define an HDX where the ground set is the edges of G, and the top dimensional faces are, I think, so spanning tree on n vertices, I guess, has n minus 1 edges, so it's something of dimension n minus 2, and these are the spanning trees, assuming G is connected. And then you close it downwards, and then we saw that if you want to understand this random walk, it's just the down-up random walk on this HDX, and to understand this down-up random walk on the HDX, all you need is to understand the links. Because of this equivalence, if you want to prove expansion here, it's enough to prove expansion here. So you need to understand the structure of the links, and they turned out to be very easy to understand. I don't think we did it completely, but it was easy. So it boils down to bounding expansion of links. So we got this theorem which solves a decades-old conjecture. I think it was from the 90s or so, I'm not sure. Kind of came naturally from this point of view. Okay, and then I'm jumping ahead a little bit, and this is something we did Max did in his lecture, and we did also maybe one lecture before. And this was doing a kind of, pseudo Fourier analysis. Analysis on HDX. Basically, we showed how any function on the I faces, let me call it the K faces. Okay, any function on the K faces can be written as sum of a bunch of functions where I goes from -1 to K, I guess. So the function has different components, and these guys, Fi is roughly orthogonal to Fj, so everything is approximately. So this is a decomposition. Maybe I should write it better like this. Fi belongs to a certain linear space Vi, which is an approximate eigenspace. And when I say eigenspace, eigenspace is of an operator. If you have an operator, you can talk about the eigenvectors and eigenvalues. What is the eigenspace? What is the operator? So for example, you can think of the up-down or the down-up or any variant where you mix and match these U's and D's. As long as you go back to, you start at level I, you should go back to level I. So Vi is an approximate eigenspace of these guys, and the VI's are also roughly orthogonal. I'm going to write it like this. And there are several different ways to do the decomposition, but they all roughly achieve the same kind of thing. And the nice thing is that each VI has its own lambda I. It only depends on the laziness, basically. So for all simplicial complexes that are lambda HDX, the eigenvalue is roughly up to this lambda, something like 1 over I plus 2 or something, depending on which operator I'm looking at. And we also saw that this also generalizes to partially ordered sets. So we don't need to be talking, when we talk about the up and down operator and we talk about this decomposition, we don't need to be talking about simplicial complex. We can actually be talking about a more general poset. For example, one poset that we like is the Weizmann poset, which consists of all subspaces of a vector space, in particular of a finite field. Okay, good. And last week, Max showed us how to push this much further and use this kind of ideas and continue to kind of study the analogy between functions on the Boolean hypercube and also on the very, very biased Boolean hypercube, and functions on HDX, either often, I think in Max's lecture it was always K-partite HDX. And we said that you can study small set expansion via tools that are called, let me say, just hypercontractivity. Max proved the Bonamy lemma. He proved it only on the, well, the Bonamy lemma is for the Boolean hypercube, but you can take these proofs and kind of adapt them to this setting. So we didn't do it completely, but it's something to know that if you need to understand expansion of small sets and so on, then this can be done. And in particular, we also talked about the kind of the non-expanding sets. Who are the non-expanding sets? So these are basically the links. So, you know, all K faces containing a vertex is a kind of set that if you go up and down, you're not going to lose it so much. So we talked about that a little bit. I'm not going to go into that. Okay. Okay. Then, so this is kind of a summary of, to me, the way I think of the part of HDX that kind of relates to these two items. How you think of graphs spectrally, and how you think of random walks, and how you think of the Chigger constant, and combinatorially as expansion of sets, although this last sentence probably applies here as well. So this part, when you generalize it to higher dimensions, this is the kind of thing you care about. And now I want to talk a little bit about the third part, but I thought before that, let's remind ourselves of some constructions that we saw of high-dimensional expanders, because I just erased the sentence that says it's not so easy to get high-dimensional expanders. But maybe it's just a matter of time, because it used to be that people didn't know how to get expander graphs, and now we think that they're so we understand them, and it's easy to construct them. So maybe HDX will follow a similar route. I don't know. So, but let me anyway write constructions of HDX. Okay. So I guess the first construction really one should think about is the complete complex. So, let me call it X. Let me call it delta. I don't remember actually the notation, but let's do it like this. So you have n vertices, and you have all possible d+1 sets of this guy. So n vertices, all possible sets as top faces, and then you close it downward, and we saw, this has wonderful expansion and so on. Another complex that we saw was the spherical building. It's just a name. What was this? It was, you look at a vector space over a finite field, so fp to the m, and you look at all possible subspaces. So the vertex set, x0, has many different subsets. It's really colored. There are sets of different colors. The colors correspond to the dimensions, so it's, I guess, I don't know, V1, maybe V0. Okay, V1 union V2. This is a disjoint union Vm minus m-1, where the Vi are all linear subspaces of dimension I, subspaces of f to the m, yes? So this is just the vertex set, and then the top faces x, how many do I have? m-2 here. This is just the chains, what we call the flags. So these are V1 contained in V2 all the way to Vm-1, where Vi is a subspace of dimension I. So this is a HDX, and you can wonder whether or not, well, it's a simplicial complex. You can wonder whether or not it's an HDX. But actually, okay, we didn't give it as exercise, but actually if you want, you can use the link definition. You can look at the links of this thing and convince yourself that it's a very good expander. So that was this example. And one of the reasons to care about this example is because the first and most famous high-dimensional expanders are the expanders, the Ramanujan expanders. Constructed by Lubotsky, Samuels, and Vishne, and by others. And these guys, we didn't study them. They involve much deeper math. They come from something that's like an infinite object, so like the infinite tree in dimension 1. When you quotient it, you get good Ramanujan expanders. So when you go to higher dimensions, you get something that's called the building, the Brod-Titz building. It's also an infinite thing. It's an infinite simplicial complex, and when you quotient that, whatever that means, we didn't discuss it, you get a constant degree simplicial complex. It's connected, and the link, so for every vertex in this complex, the link looks exactly like the spherical building. So many things that were proven, especially in TCS, on these objects, this is all the information that they needed. They don't use any deeper understanding of the object except to know that its links look like this. Because of things like the trickling down theorem, it's enough to know that the link is a great expander to already be able to prove a lot of nice theorems. Okay. The construction that we did see is the Kaufman-Oppenheim coset complex. This is a constant degree HDX with links expanding as strongly as you want. And we saw this, Yotam gave this lecture. We started with some group. In that case, it was SLD of some ring. It was a group of matrices. But the interesting thing is that you take some subgroups in this group, H1 up to H, maybe D, and the cosets of these subgroups are going to be your vertices, and you connect two vertices by an edge if the cosets intersect, and you connect three of them by a triangle if three intersect, and so on, and you can prove that they satisfy, for example, the link expansion definition. So this is group theoretic, but it's pretty elementary, so if you want to understand some construction, I think this one is a very good place to start, and in particular there's a paper by Harsha and Saptarishi that give a very nice elementary analysis showing all the expansion and everything, so this recommended. Okay, and then we also saw the left-right Cayley complexes. And this was not a simplicial complex, it was a square complex. Remember, we had the group, we had generators, we created the Cayley graph by multiplying both from the left and from the right, and then we had the squares where you go left, right, left, right. And we use these to construct codes and so on, but you can also think of it as some interesting construction of a two-dimensional object. It does not satisfy any of these properties, so it's not a simplicial complex. Okay. And there are many other constructions that we didn't cover. Siki gave a lecture not too long ago about let me write just we didn't cover. So there is this construction of comes from sampling the high-dimensional sphere. This is a construction Siki discussed. You can construct complexes, let me call it the paths complex. starting from a graph, from an expander graph, and then you can take paths of length d as your d faces and go down, and there are more constructions. There's a construction that you can think of as coming from codes. Yotam has a very nice construction coming from lifts, or let me say random lifts of high-dimensional expanders. But of course, my feeling is that we haven't yet kind of fully uncovered the potential here, and I think this is a very interesting direction to try to come up with other constructions. In particular, we would love to have something analogous to the zigzag construction. So there is a construction of expander graphs that starts with a constant size expander graph and keeps growing it. And it's elementary, right? So it would be wonderful to have something like that for HDX. We don't know. We have some works that construct codes from HDX, and we know how to construct expander graphs from good error correcting codes, so maybe we can construct also HDX from good error correcting codes. I don't know. And anything else is also interesting and open.
So if you start from a small even HDX
Mm-hmm.
and you do zigzag process, it will not be HDX anymore.
If you do the zigzag, yeah, you will kind of open your triangles and you won't have any more triangles left. So
It kind of makes sense.
yeah, kind of the simple ways to do it, they all fail, but no, all is the incorrect word. Some simple ways to do it fail. Maybe we just haven't exhausted everything. Maybe there's a deeper reason why you cannot do it, I don't know. But okay, I'm not sure about it. I used to think there's no way you can do it, but now I'm less sure of that. Okay, I had some more examples I wanted to talk about. Of course, the matroid, I have it up here. The complex that you get by looking at all the spanning trees, this is another example of an HDX. It's not constant degree, but it's polynomial, at least the top is polynomial degree. The bottom is certainly not, so I don't know. Okay, so...
Can I ask a question?
yes, please.
In graph expanders, we typically talk about how good the expander is, like how small lambda is compared to the Alon-Bopana bound. And here in these constructions, we didn't quite discuss like their optimality or...
Okay, great question. So optimality. And is there an Alon-Bopana bound? Alon-Bopana says that the second largest eigenvalue cannot be so small. It has to be a little bit big. And I know there is some work by Liniel, Chapman, and Peled, I think, that talk a little bit about this for HDX, but I don't remember what they proved. I'm sure there's a lot of still unknowns there. There are these complexes that are Ramanujan. They're optimal in some respect. What is this respect? For the infinite tree, we know the spectrum of the infinite tree, and we know that when you have a finite object, you must have one eigenvalue of D, but all the other eigenvalues are strictly below this infinite object. Similarly, this is what happens for the higher dimensional case. We know, or people know, the spectrum of this infinite building, and the Ramanujan complexes, they have just these eigenvalues plus the ones that they have to have. So that's optimal in that sense.
But
I don't know.
Talking about eigenvalues of the up-down operators or of the skeletons or...
Of all of them together. And I doubt that, I mean, this is a very rigid structure, so I think if you just think of a less rigid structure, it's probably, okay, it's actually it's worth studying. I really don't know what's going on there, and I think it's an interesting question. Yeah?
There is a theorem, maybe not so known, of Winnie Lee, which is a Lombopana in ion dimension, for the LSV in the following sense. You think of the Brotitz building as complexes with color, and you take the coloring also into the game, and then and then instead of having one Laplacian, you have color Laplacian. You have like d-1 color Laplacian, and they are all commute with each other.
Right.
So they have a joint spectrum, and this joint spectrum is not a number anymore, but it is a vector in C to the d-1. Okay, again, you have d-1 operators, all commute with each other, and therefore they have a joint spectrum. So the joint spectrum, so each eigenfunction to all.
Okay, so these are, you have these operators, A1 to AD.
In fact, there is some kind of repetition in the sense that it's better to, it's A1 up to A.
Should I call them H?
No, these are
Hecke operators, okay.
Up to H d-1.
Okay.
And,
So I have D colors.
they are defined like that. If you want the precise definition, is hi of a function is on a vertex x is a sum of all f of y, all the neighbors whose color is the color of x plus I. So the coloring of y is the color of x plus I.
Maybe mod D or something. Okay.
Yeah. And then, okay, one can see, for example, that hi. Now, the problem with them, that they are not self-adjoint, but they are normal. Namely, in fact, hi equal to hd minus I star.
Okay.
But they are normal and they commute with each other, so they are all diagonalizable together.
Right, and for certain eigenfunctions f, you have really lambda 1, which it's the same eigenfunction, so f corresponds to this lambda 1, lambda 2 up to lambda d minus 1.
And inside the space c to the d minus 1. Now, here is the beauty of this of this version. You have to think of Alombopana in the following sense. Why Alombopana said that the best is between minus 2 square root d minus 1 and plus, because this is the L2 spectrum of the infinite tree. So now you take the L2 spectrum of these operators on the Brotitz building, and this is an object in C to the d minus 1, which was computed by people because of representation theory issue. It's a non-trivial issue, but it was known for many, many years. And now, if you have, you have a set of finite complexes. You have a sequence of finite complexes. Each one contributes finitely many points like that.
But now you're assuming that my finite complexes come as quotients of the building. So this whole theorem is relevant for a quotient of the Brotitz building.
Each one of them contribute finitely many vectors to the collection. Now take this collection so you have a subset of c to the minus 1. The Winnie Lee theorem says that if you have infinite collection, well, which converts to the identity of the diameter with some technical condition, which is basically inside always the closure of this countable set.
Is inside this set.
Not just inside, contains. No, it's inside because the Ramanujan. But if you take
It contains the entire spectrum of the building.
It contains that basic
Okay.
set. It's like saying that for an infinite collection of graphs, the spectrum of them, the closure of the spectrum contains the interval, might be bigger than the interval if they're not Ramanujan.
Yeah.
But it's at least this one.
Yeah.
Alon said that it's at least this, right? And so this is a kind of even a strong version of Alon Bopana in some sense.
In some sense, but it's very specific to quotients of a specific complex. And as opposed to the graph case where every graph is a quotient of the infinite tree, here not every complex is a quotient of what it's building. In particular, the links are not necessarily spherical buildings.
But I believe that the following should be true, and that's the Alon Bopana, the ultimate Alon Bopana, because not always we have the coloring. So probably one should say the following: take a finite simplicial complex, and by the way, Alon Bopana like that is known in graph for non-regular graph. It's known by now. But take the universal cover of it. Now take all the quotients of this universal cover. Take all the different Laplacian, the first, the second in the higher dimensional. Compare them to the spectrum of the upper Laplacians in the universal, and this should be the right Alon Bopana.
This is a conjecture.
Nobody proved.
This is a good way to start. If you know how to define these Laplacians, because it's not so clear that you will have, like in the Hecke operators, that they will commute.
Right,
It's not clear that you have the whole thing.
Higher dimensional Laplacian, like the discrete Hodge theory, you have Laplacian, like the one with the cohomology and all that. So that's could be a nice.
Okay, yeah, that is a nice project. Okay, good. All right, thanks. Okay. Right, so let's take a break, and then after the break I just want to summarize the second part of the course, which is the definition of cohomology, the connection to property testing, locally testable code, quantum codes, all this stuff. We can do that after the break. Okay. So, so the second kind of part of this topic that we studied had to do with the cohomological definition of expansion. Okay, cohomological expansion. And this has to do, so I guess some people would say it has to do with topology maybe. I kind of feel that it has to do with linear algebra. Everything here has to do with linear algebra, so when I say that I really mean over like F2 or something like that. So it's some kind of a way to connect the geometric structure of our complex to some system of equations or something like that. So the way this definition works is that we have a complex, we think of the different layers, x0, x1, x2, and then we think of Boolean or F2 strings or assignments on these faces. So what I mean here is that this is a string of bits where I put a bit on every vertex. This is a string of bits where I put a bit on every edge and so on. And then we looked at the geometry as providing us with kind of linear maps that go from these kinds of strings to these kinds of strings to these kinds of strings. These were the co-boundary maps. Let me call this delta 0, and this I'll call delta 1, and you can keep going. And of course, we also had the joint ones. These were the boundary maps. But I'm not going to talk about them. And the same, I guess I erased it. Remember, I had here on the right, I had this bipartite graph for the up and down walk, where I put here xi plus 1, and I put here xi, and I connected s and t if s contains t. So the same adjacency structure defines these guys, where you define a delta of a function here at a point s to be. Previously we did expectation. Now we're just going to do the sum modulo t. You're defining it at s by taking all the neighbors and summing them up, summing f on the neighbors. So you're using the exact same adjacency structure. I guess delta f at a point s is equal to the sum for all t less than s of f at t, right? This was the definition of the operator delta. And unlike what we had before over the reals, here it's like mod 2, if we were doing f2 coefficients. And here we had this nice property that if you apply delta once and then you apply delta again, you get 0. So we had this, I guess I should do it like this, delta 0 and then delta 1 is equal to 0. In other words, it means that the image of delta 0 is contained in the kernel of delta 1. And this property is what we call more generally, even if you have a chain of linear maps that don't necessarily come from a geometric object, you can always think of this as a chain complex, where you have this property. And this turned out to be very interesting because it allows us to study linear maps in higher dimensions. Here, one way to think of these two linear maps is to think of them as one object that has 2 dimensions, right? These 2 parts. And the expansion has to do with both of them together, right? And this, I guess I have this written just up here. The expansion has to do with how much do you violate being in the kernel, meaning you have some function here, okay? You apply delta to it, and you want to get 0. If you got 0, it means this function was in the kernel of delta 1, okay? So the weight of delta of your function is some kind of test of how much violation you have. This is what's written over here, delta of f. It's measuring how many of the constraints that you want to be 0 are actually 0. And then you want to compare it to something else. You want to compare it to whether your function is really in some good set. So the good set, in this example, it's the set of constant functions, but in more generality, the good set can be all the functions that came from one step below, like the guys here in the image of delta 0. So that was the general definition of a consystolic expansion. So let me remind us. So we defined consystolic expansion to be the minimum. Now I'm going to take F to be an I chain, so let me call it Ci, but I'm not going to allow it to be in some set that appears here in the denominator. I don't want to divide by 0, right? So this set is really the kernel of delta I. So here it's the kernel of delta 1. And we also had another name for it. These were the co-cycles. We called it Ci. And the consystolic expansion says, okay, delta I of f, I'm going to measure how many times this constraint is not 0, so delta I defines these constraints, and I'm going to compare it to the distance of f to the kernel of delta I. Okay, this was the cosystolic expansion. Of course, if f is inside kernel of delta I, this is 0, and makes no sense, 0 divided by 0. And there was some, if the kernel of delta I is equal to the image of delta I minus 1, meaning here I had equality, it means that everything that's 0 when you go here is really because it's coming from below. And then you say that this chain is exact. If this happens, then we say that this is we have co-boundary expansion. So it's just the same definition, but when you know that the kernel is really things that come from below, you say that this is co-boundary expansion. Otherwise, it can be some things in the kernel of delta I that don't come from below. Okay. And this is kind of a very strange definition for people who don't study homology, but it turns out that it's very much connected to property testing and local testability. And we saw this interpretation. So we saw this property testing. This is due to Tali and Alex interpretation. Really that delta IF measures how many local tests fail. Okay, so what is delta IF? If I'm on a simplicial complex, f, for example, might be a function on the edges, and delta IF is a function now on the triangles, and it's really taking, for every triangle, it's summing the function on the 3 edges of the triangle. So this just says on how many triangles does f sum to something non-zero. This is what this means. Okay? And so I can think as if I'm looking at a function and I'm making this test. I'm reading the function at the 3 edges of the triangle and asking myself, did I get 0 or not? So this numerator just asks how many of these triangle tests fail. And what's happening here? Here it says, well, this is the definition of the expansion constants. Let me call it HI. I don't know, HI of x. It's the expansion constant. Now, if this constant is big, it means that these two things are proportional to each other. So it means that if this is small, this must also be small. What is this? This is the distance of your f, your function on the edges, from kernel of delta I. What is this? This is like your property. So here, kernel of delta I is some property. For example, it can be the property. In our case, it's the property of a function on the edges that sums to 0 on every triangle. It's a subgraph that is 0 on each triangle. Okay? This can be our property, and the fact that this is, say, bigger than 0.5 or bigger than 0.1 means is that if a few triangles fail, you must be close to a function that is really in the property. So you can correct your function to make it in the property. And this is what property testing is. You have some property. In this case, it's a very specific one. Property testing is much more general. You have some specific property, and you want to test by reading just a small part of your f whether it's close to the property or not. And this leads to a hope of getting locally testable codes from from this kind of construction, because we've already seen that you can get very good codes from expander graphs, and so maybe using this extra dimension, you might be able to get good codes that also have this local testability. And indeed, we saw that. We saw that in this. Saw this for the squares complex. Gives this squares code, and we even saw that you get something very different, which was this quantum LDPC codes, which we discussed, but I want to see if I'm missing something. Okay, I'm not going into this too much, but the quantum LDPC codes, what was going on there was that you had your quantum bits, and you had one map that does like your X parity checks, and another map that does your Z parity checks. And really, the way it's set up is that you end up getting 3 vector spaces, and you really have one a chain of 2 maps going this way, and there's a dual one going this way, and you can think of this as delta and this as D. And your quantum code sits here, and it's really just this kernel of delta I object in the middle. So it's really just this space in the middle between the 2 chains. And what was interesting that we saw was that a lot of theorems we kind of could prove in a very similar manner. So basically we had a bunch of theorems that one was cosystolic expansion of HDX, basically proving under certain conditions the map, if you have an HDX X, it's a simplicial complex. It's a link expander, for example, and if you know something special about its links, co-boundary expansion, then you can prove that this complex has cosystolic expansion, and we discussed this proof a little bit. You can also prove the LTC-ness of the squares code, which at least sounds very different, but really inherently it was the same proof idea, showing that if certain tests here fail, you must be able to take your function and correct it and make it into a perfect code word. That was the LTC-ness. And there was also the distance of the quantum LDPC codes, which all of them rely on very similar logic, I would say. And all of them are kind of local to global. And they have really 2 components. One is kind of a global mixing of random walks. Some global thing is a good expander. And local, you have some good co-boundary expansion. If you remember when we talked about the squares codes and stuff, then the local object was this tensor code. We talked about tensor codes. Actually, tensor codes themselves, even though they're local objects, you can think of them like this. As a 2-chain, you have a k by k message. You first encode the rows and then the columns, or you first encode the columns and then the rows. And we saw that there is some notion of co-boundary expansion for tensor codes, which is also called agreement. I don't know what we called it, agreement testability. So we saw a bunch of notions that are very related. I'm not going to go into the definitions. I guess from a high level, my point here is that I think this is, to me, this is kind of a new collection or direction where you take a geometric object where you know stuff like mixing and so on, and you combine it with a very linear algebraic thing. Either you have a tensor code, or you just, in the definition of delta, you're just basically summing a bunch of bits, so it's maybe the simplest local object. And you combine them together, you get a new linear subspace. You can think of it as a quantum code, you can think of it as an error correcting code, you can think of it as a property, and you're doing property testing. But somehow the testability comes from this connection of these two kinds of expansion. So I think there might be more things to say here, but this is what I have right now. Yeah, so these were these theorems. And to finish, probably finish in a few minutes, I just want to mention a couple more things and some open problems. So the last thing that I want to recall that we discussed is these agreement theorems. We talked a little bit about PCPs, parallel repetition, and agreement theorems. And there the idea was that you have a collection of vertices and you have, subsets of elements. These are the faces. And someone is giving you local assignments to the vertices, say 0, 1 colorings. But these are local. It means that this guy gets its own coloring and this guy gets its own coloring, and they might disagree on some shared vertices. And the agreement test says, okay, I take two of them that intersect, I check if they agree, and and then I count what's the probability that a pair agree, and this is some kind of agreement value. And the agreement theorem says if your agreement value is non-trivial, it's high, say it's 90%, it must be because these sets all come from some global coloring. So it's also some kind of property testing. So it's kind of a property testing. And like the case of consistolic expansion, which is a type of property testing, this is also a type of property testing that's very, very restricted. You're not allowed to do any test you want. It's only a test that reads two queries. And we saw that this is related to the fact that we want to, and this is related to the fact that we want to do it as a label cover. We need the tester to do these two queries this way so that we can translate it to certain hardness of approximation questions. And so we saw this connection, and we saw some very strong theorems like the parallel repetition theorem. And of course, it's open to prove a parallel repetition analog. I don't know even how to state it is not absolutely clear. The parallel repetition can be viewed as a certain agreement theorem on the complete multipartite complex. And we want to maybe generalize it to I don't know, sparse HDX, or to just other HDX. So this is kind of a direction that is interesting, and to me even very interesting is to see if constructions of PCPs, a lot of constructions of PCPs, in the construction you meet a lot of the friends that you meet here. The Weizmann and the complete complex and expanders, and it seems that this is not a coincidence. In constructions of PCPs you have local parts, and you want to check consistency, so you compare local parts that intersect, so that's very natural. And so it might be interesting to try to figure out how to use HDX technology to get new PCPs or better PCPs or something. So this is not really an open question, it's just a direction. I would love to see some use of HDX for PCPs. We know how to build PCPs based on expander graphs, but we don't know how to use high-dimensional expanders for these things. So it seems to beg this question. Yeah, so let me now just give a few more open questions and then we can close the semester. I guess not, maybe I erase stuff over here. So some open questions. So one was new constructions. We talked about this a little bit. Right, like zigzag, or maybe from error correcting codes, and so on. Okay. Another question that I like and is the following. An HDX is a simplicial complex that in many ways it's sparse, but it behaves as if it's the complete complex. So it's a simplicial complex that behaves like it was complete. Now I move to another poset. So I want, for example, the Weizmann poset. But I want it to be an HDX. So I want to find not the set of all possible subspaces, but rather a small sparse subcollection of all possible subspaces. So maybe I should have recalled. The Weizmann is the set of all, say, d-dimensional subspaces of f to the n. Okay? Just like a complete complex is the set of all d-sized subsets of n vertices. So this is like a linear algebra analog. And it would be nice to find a subcollection of these subspaces, just like an HDX is a subcollection of all d-sized subsets, a subcollection of the Weizmann that imitates it. So find a sparse subcollection of the Weizmann. Just put n and d to indicate the total dimension and the dimension of your subspaces. That imitates random walks on the complete Weizmann. Okay, so I'm just giving this as a specific example. Imitates it, you can find your own measure, but one measure that we like is an HDX imitates the complete complex in terms of random walks. The spectrum looks the same and so on. So I would like something. And we have more concrete definitions. We saw this when we talked about the up and down operators. So this is one open question. And one of the reasons to care about this is because you might think of defining error correcting codes on this object. So my third collection of questions is about error correcting codes. So we already saw some ways to define codes on geometric objects, and it seems that the geometry is very useful for us. It allows us to prove distance, it allows us to prove other properties like we have here, and maybe we can have more properties. So a couple of questions that I particularly like are one, multiplication codes. So Reed-Solomon codes have this property that if you take two code words and you multiply them entry-wise, so you take this times this and you write it down here. Okay, so you do entry-wise product. You will get a third string that belongs to some related code. So if this belongs to Reed Solomon with degree D1 and this belongs to Reed Solomon with degree D2, then this will belong to Reed Solomon with degree D1 plus D2, right? Because this is just some low-degree polynomial of degree D1. You multiply it by another polynomial, you get a third polynomial of slightly higher degree. So you have this property for Reed Solomon code. Can we get such a property for other codes that maybe are more like expander codes? Can expander codes have this property? So, of course they can. You can take your expander code, which you put the bits on the edges, and around every vertex, you require the code to be a Reed Solomon code. And then you will immediately get multiplication. The reason this doesn't work is because the rates don't work out. So the constructions that have multiplication, the rate is 0. I don't know how to prove that there is non-trivial rate. So this is one question. And the second question is again about expander codes. And here it can be expander, or it can be HDX, or it can be something else, I don't know. But I want that the local views. So when you define a code, like an expander code, there's all these local collections of coordinates, like all the edges around the vertex. It's a small part. And you want that in this local view, the distance of the code will be large. Somehow this might feel like an arbitrary requirement, but it's going to be very useful for many other applications down the line. So large distance, close to 1. Okay, so this is another question.
Can you understand what you want?
Let me give an example for expander codes. In an expander code, I have my graph, and the bits are on the edges. So my code says if you want to be in the code around the vertex, these set of bits need to belong to some small code C0 for every vertex, right? So now I want C0 to have distance close to 1. Close to 1. Very high.
Family of expanded up which are not LDC.
They're going to be LDC.
I mean,
LDPC, you mean?
because the degree is going to infinity.
No, don't, no, I see. No, let's say distance 0.8. Okay. Above a half. Okay. Later on, we can also push this parameter to go to 1, but it will go after everything else went to infinity.
But that's the problem to do it kind of inductively, take every code with large distance, put it.
Okay, what's the problem? If I have a code with large distance, what can I say about the rate of this code? It's no more than 0.2, even less than that. If the distance is very large, the rate is no more than 0.2. That's the main problem. And in all of our analysis on codes, when the local rate is tiny, we don't know how to prove that there's any code word left. So really, this is the heart of the problem. You want that the local rate is tiny, and yet there should exist code words. So this seems to be related also to constructing PCPs and other things.
Sorry.
Yeah.
For multiplication, didn't the tensor codes that we discussed have this property and they kind of expanded for agreement tests?
Tensor codes don't have this property. So a tensor, if I have two code words, a code word in a tensor code looks like this, right? It's like a n by n string, and I have two of them. Then if I want, now I'm going to construct a third matrix where this entry will be the product of these two. So the only way it will be a valid multiplication code is if the row code and the column code are themselves multiplication codes.
Always.
Yeah, but so if I already had that property, I will maintain it, but I'm not getting anything new.
Okay, it's different from agreement, basically, because they're in agreement, basically.
Yeah.
Okay, it's a little bit different, basically.
Yeah. What else? Okay, another question also we discussed over the break is we talked about the trickle-down theorem, and in some cases, like in the spherical building, strong, I don't know if strong is even the right word, trickle-down theorem. So I would say it's specifically for the spherical building. In the spherical building, you can look at the link. You have some graph. It's a bipartite graph, and we know the expansion, and it's actually very good in terms of the relation between the degree and the spectral gap. Then you look at larger links, like now it's a tripartite graph, and you have these triangles. And if you look at the underlying one skeleton, you will see that the spectral gap is even better. The spectrum of this larger link, second largest eigenvalue, is much smaller than the one you had here. And if you go to a bigger link, now you have a four-partite, it will be even better, and so on. It keeps improving. So I'm saying that the lambda 2 of link of S in xi is smaller for smaller I. Much smaller. But the trickle-down theorem doesn't promise me that. It just promises me that it's not much worse. It never promises me that it gets much better. Okay? So is there some properties or some way to capture this more generically? Like, are there some conditions where you can prove, if my complex has this and that, I can prove kind of an improvement. Not only it doesn't get worse, it actually improves. Some kind of amplification, I don't know. Amplification. So it's another question. What else do I want to say? There's another, okay, one more question and that's enough. So this is somehow related to Tashma's codes. There are these error-correcting codes where you have an expander graph, you put the bits on the vertices, and then on every edge you write the XOR of the value on the two vertices. And you show that if you have a function, say it's on the vertices, if you know that the bias of this function is small, then now you look at delta f. This is when you XOR on every edge, and you see that the bias of this guy is even smaller. I think it's maybe like epsilon times epsilon plus lambda. I'm not sure. Okay, so this XORing improves your bias. What happens if I take an HDX and I look now at triangles and I want to XOR the three bits on every triangle? So it's not this delta operator. Let me call it some new operator D. So df is a function on a triangle, UVW, which is defined to be f of u plus f of w plus f of v. I don't know why I skipped v. Anyway, I'm defining this new function on every triangle, and I want to know what is the bias of df compared to the bias of f. Bias, by the way, if f you think of it as like 0, 1, it means you're roughly half-half. There's a bit more zeros or a bit more ones. Okay, so do you get something of the order of epsilon cubed? Or do you get epsilon cubed plus lambda epsilon? Or do you get plus lambda epsilon squared? What's really the error term that you're supposed to pay here? So hopefully it's something cubic and not quadratic, but we don't know. So okay, that's a question I like. Okay, next semester, which is after Passover, so it's a long time from now, we will have a seminar on some topics on HDX, so co-organized with Alex maybe. It will be a seminar, not a course, so we'll have various speakers, and you're welcome to come and to suggest topics that you want to hear about. I think that's enough for the recording.